All right, so today moving into viewing the derivative as a function, which it is. So in the last section, we were looking at calculating the derivative at singular points using that shrink wrapping idea of bringing the slopes of the secant lines down to the tangent line, where it's just touching the curve, or we're just talking about the instantaneous velocity instead of average velocity. So for relatively reasonable functions, we can not just do this at a arbitrary point that we pick, like we said, t equals 3 seconds, um, or at x equals 2, whatever it was. We can now say, let's do it in the general case. If we can do this at these arbitrary points, that means we can do it at any point. So what we're going to do here is look at this exploratory example a little bit, and then move into looking at the definition of the derivative as a function. Okay, so let's kind of remember what this notation means. So f prime of x means the instantaneous rate of change of the function f at the value x. Okay, like before we said it'd be at some constant a, but now we're saying we want this to be at the general input for any x that we stick into it. So it's the instantaneous rate of change. It's also known as the derivative of f. Derivative of f at x. Okay, so f prime of x. And again, it has an output at each input x. And what that output is the slope, or the instantaneous rate of change, the slope of the tangent line of the function f. So there's kind of this like tethered function. So if we have x and it gets mapped to f, there's also this kind of tethered function, f prime, that tells us about the instantaneous rate of change of f. So it's kind of this like invisible function that's been here all along that gives us information. We can kind of think of it as the speedometer of f of x. That's what f prime is. Okay, the speedometer of f of x. So with that being said, let's explore a bit through this example. So we're given a table of values, so we're going to look at this from the numerical perspective, and it's asking us to estimate f prime of 2 using the values in the table. So f prime of 2 means at x equals 2, which would be right here. Estimate f prime given these values of f. Well, what is f prime? F prime is the instantaneous rate of change of f at x equals 2. So we can't really get exact here, but we can get pretty close. And what would be our best guess at this would be maybe we measure the instantaneous rate of change, or the average rate of change, sorry, here, and the average rate of change here. And that would give us a good picture of what's happening, before and after x equals 2. All right, so we'll measure the rate of change here, and so that's 18 minus 10 over 2 minus 0. So if we wanted to write this out in function notation too, this is f of 2 minus f of 0 all over 2 minus 0. So this gives us 8 over 2, which is 4 over 1. So that's the slope kind of moving towards this point. If we sketch this out, we're interested at x equals 2. From 0 to 2, we know something like this is happening. It's going up at a rate of from 10 to 18. So it's going up at a rate of 4 over 1. And then from 2 to 4, it goes from 18 to 24. So for that change here, f of 4 minus f of 2 over 4 minus 2. Again, it's 24 minus 18 over 2, which is what? 6 over 2, which is 3. So something like this happens where it's not as steep as from 0 to 2. It's doing something like this. And then again, this isn't really the curve, right? The curve could be doing something like that. All we have are these points here and here where we can talk about the average value, right? But all we can do with the information we've got is give a best guess for what the value of the derivative is here. And so it'd be the average of these two things. We'd say, well, with best we've got, because I could sketch a billion different curves going through here, but as best we've got with this table, we'd say it's somewhere in between these two. So we could say 4 plus 3 over 2 is a good approximation, and that's 3.5. Okay. So the idea here for A is that we're able to estimate the instantaneous rate of change with the average rate of change. So now we're asked to open up our lens a little bit with f prime of x on the whole table. It's asking for what values of x does f prime appear to be positive and negative. So now we're talking about the sign of f prime as a function. So what does that mean? It means, if f prime is positive, means that the slope of the tangent line is positive, which means that f of x must be increasing. And just the opposite if it's negative. F prime of x being negative implies that f of x must be what? Decreasing. Because if the slope of the tangent line is negative, that means it's going down. Just other way around for when f prime is positive. So here we can just really take a look at the change. We see that x is going up in equal intervals, so that's fine. So we can see, is f increasing or decreasing on these intervals? So here we see a positive change. So it's increasing here, increasing here. Looks like it decreased here and decreased here, decreased here and decreased here. So we can say then that f prime appears to be positive for x equals 0, 2, and maybe 4. And then again, you do this at to get an idea of what's going on at 4. It's increased by 6 leading to it and decreased by 3 going away from it. So, our best guess is that it's closer to increasing than decreasing there. But again, we're working with imperfect information. And then f prime appears to be negative for x equals 6, 8, 10, and 12. You could write these as intervals as well, but that's all fine. Okay, so again, the idea I'm trying to drive home here is that f prime itself is a function. Okay, if you input x equals, what do you get out of f prime? You get the instantaneous rate of change of f. So again, this is the speedometer of f. So just like in a car, you've got the odometer, that'd be f. That kind of tells you your position. This is a very rough guide to this idea. And the speedometer is f prime. So that's why it makes sense that if you have your f prime and the sign is positive, that tells you that you're increasing. If it's negative, and again, it's kind of a velocimeter really, but we don't call that in the car, then you're going backwards, right? That's like going in reverse. Okay, so I feel like that's pretty clear now. So I do want to give you the definition of the derivative, which you're going to need to use quite a bit to drive home this idea. So this is how we've defined the derivative. It says the instantaneous rate of change of f is the limit as the time interval goes to 0 of the change in the quantity over the time interval. Okay, it really just is the instantaneous rate of change. And so we're going to do this for a very simple function, just the parabola. All right, so let's find if f of x equals x squared, find f prime of x. And we said this is the limit as that time interval goes to 0 of f of the later quantity minus f of some earlier quantity for all x all over the time interval. And so, again, here we plug in x plus h into our function, which is just x squared. And I dropped my limit notation here. Limit as the time interval goes to 0 of x plus h squared minus x squared all over h. And so don't be tempted to just square things indiscriminately. You do want to expand this out all the way. Okay, so you see this piece here is this piece here. And so then we're left with the limit as h goes to 0 of 2xh plus h squared all over h. The x squareds cancel. And so this is generally how these should go. You should have a factor of h left over so that when you can write it like so. And we've seen this before. 2x plus h in the top all over h. These h's cancel only like this. So this is the limit as the time interval goes to 0 of 2x plus h, which, again, that h going to 0 is not going to affect the 2x. It's going to drive this to 0, and so you'll just be left with 2x. Okay, so what did we just find? Follow the string of equality. We started here. We followed through what we call the definition of the derivative, and we ended up here. And so what that tells us is then for f of x equals x squared, this function, f prime, its speedometer is 2x. Okay, so this is a pretty fundamental derivative function, and we just proved it to be true. And so what this means is that at each x, at whatever it is, x equals a, so you can, make up any value you want. Let's say x equals a. We know that the height is given by a squared, and the slope of the tangent line aka the slope of the curve at that point, or the instantaneous velocity, is given by 2 times a. Okay, so again, you have two pieces of information about this function already. Just knowing the function's rule, just knowing x squared, you already know that the derivative, the slope of the instantaneous, the slope of the moment, slope at that tangent line, is 2 times the input. Okay, so let's go ahead and derive some of these important formulas we're going to use. I'm going to do 3 of them right now, and then I'll leave the rest for you guys to work through, because they tend to be the same. It's just working out through the algebra. All right, so we've actually already done this guy, so we don't need to work through that. But let's look at this one. So if f of x equals 1, then f prime of x is equal to what? Well, wherever I plug in my input, right, we're taking that time interval. I want to plug in x plus h, subtract f of x, and then divide by the time interval h. So where do I plug in x plus h into the function f of x? Well, it doesn't have a space for the input in the rule. It's just a constant 1. So it's equal to 1 at the input x plus h, and it's equal to the input 1 at x, because it's just a flat line, right? So it doesn't matter where you are, the height is always 1. So this becomes 1 minus 1 all over h. Trying to jump to the fun part here. 1 minus 1 over h, which becomes just the limit as h goes to 0 of 0 over h. Right? And what happens here? Well, this really just simplifies to 0 before we take the limit. Right? So this becomes the limit as h goes to 0 of 0, which doesn't have any effect on the time interval, so we really just get a limit of 0. So what does this tell us? Again, follow the string of equality. It tells us for f of x equals to 1, f prime is equal to 0. And so we can generalize this in the following way. For f of x equal to some k constant, wouldn't this work out the same exact way? Because 1 was just 1, but if this were equal to 5, this would just be equal to 5 minus 5, and we'd still get the same result. Or if it were, trying to undo here, or if it were, 700, well, then when we go through the definition of the derivative, this would be 700 minus 700, and we'd still get 0. So this works in general, that if the function is a constant, then f prime is 0. And why does that works out algebraically, but how does that get reinforced by our geometric understanding? Well, f of x equals k is a flat horizontal line, so it has no slope. Right? It's got no grade to it. Okay, so let's that's a fundamental one that you're going to want to memorize, that the slope of a constant function is 0. So when we differentiate that, you don't have to recreate the wheel every time. But we're going to start off by deriving these each time. So that's this guy, that's a. So let's do d. So I feel like that's some algebra we don't see often. So for q of s is s cubed. Oh, let's use the proper notation here. So this would be q prime of s. This is going to be the limit as h goes to 0 of q of s plus h, that time interval, minus q of s, all over h. Okay, so what is q of s plus h? Well, we take s plus h and plug it into the function. So that's s plus h cubed minus s cubed all over h. And again, I dropped my limit notation. Just going a little too fast. So here we'll expand this all the way out. If you don't have that memorized how to do it, that's okay. You can break it into pieces. Remember, it's really just 3 of these factors. All over h. Okay, so that's s plus h, s squared plus 2sh plus h squared, all minus s cubed. And then you're going to distribute this through here. And so you'll get s cubed plus 2s squared h plus sh squared, plus, and then distribute an h through, s squared h plus 2sh squared plus h cubed. That's just this piece here. Then we've got that minus s cubed all over h. And so let's combine some like terms. You know the s cubes go away. We've got now 3 s squared h terms, so let's jot that down. It's got this guy and this guy. 3s squared h plus 3sh squared plus h cubed all over h. And again, we'll pull out an h from the top. Those will cancel. And so you're left with the limit as the time interval goes to 0 of 3s squared plus 3sh plus h squared. So as the time interval goes to 0, this goes to 0, this goes to 0, and this goes to just 3s squared. It's unaffected by that. And so that's our limit, 3s squared. So again, I keep reiterating this because I think we can get lost in the string of equality sometimes. We see that q prime of s is equal to 3s squared. So what that tells us is that for q of s equals s cubed, its speedometer is 3s squared. Okay, it's another one to jot down. In general, I'm also going to generalize this. Okay, so we saw that, let me add on a blank page here. So we saw that for f of x equals x squared, that f prime was 2x. We saw that for, I'm just going to rewrite it in terms of f, for x cubed, the derivative of that function was 3x squared. In general, if you have a power function, it's always going to work out in that same way. And you can do it for a few higher degrees. It becomes a little tedious. I had to do it back in my day, but I won't force you to do it. But unless you're really curious about this pattern, what do you think happens? Well, what happens is that you end up losing a power. Let's say that the slope of the function is described by the power function just beneath it. Okay, so in other words, the parabola is described by a line, the cubic is described by a parabola, and the nth degree power function, its slope is given by 1 power down, n times x to the n minus 1. Okay, so this is the general rule. It's what's called the power rule. And a lot of people learn it before the definition of the derivative, but it only really makes sense coming from this limit definition. This is a dangerous rule because it's so simple, but it's obviously very powerful, and it tells us a lot. And I think it's incredibly interesting that the power functions are related in this way, and that we really didn't learn about it until now. That that a power function's slope at any point is given by a power function that lives before it in the series. So that's pretty neat. So this is, again, one to jot down. All right, so I said we'd do 3, so let's do one more. Which one is this? E. F of t is 1 over t. So what is f prime of t? Well, following the limit definition, this becomes big F of t plus h minus f of t all over h, which is the limit of 1 over t plus h minus 1 over t all over h. All right, some of you, I can feel the sweaty palms out there with fractions and fractions. Don't worry about it. So, right, just follow what we know about rational functions. Get a common denominator in the top. It's one way to go. So I'll get like this here. So multiply this guy by t over t. Multiply this guy by t plus h over t plus h. And so we'll get t minus, use brackets here, t plus h all over t times t plus h all over h. I had a little hiccup there. So Again, let's go ahead and simplify this thing down. I think I was saying it might have been a while since you've dealt with fractions in this way, but that's okay. Just hang with it. So the limit as h goes to 0. We'll simplify the top. T minus t plus h is going to leave us with negative h in the top over t. Let's do it like this. T squared plus th all over h. Okay, so I distributed this through. And then let's rewrite this in a more helpful way, which is, this is a theme through the course of rewriting something algebraically to make it go from very difficult or even impossible to becoming a simpler problem. So a better way to write it, for example, a over b over c, I'd rather write this as a over b times 1 over c. And that's what I'm going to do here. All right, so this is something I see a lot of students get stuck with, this particular principle of fractions. And now you can see, oh, hey, I can cancel an h, right? Which might not have been super clear before. So then from here, I've got the limit as that time interval goes to 0 of negative 1 over t squared plus th. And we see that, you know, everything in here is really, they're continuous functions. And so, you know, this negative 1 is unaffected, this t squared is unaffected, this term is going to go to 0. And everything else is okay. So we'll be left with just negative 1 over t squared as our derivative. So what does this tell us? This tells us that for f of, let's write it in the general case, so just for f of x equals 1 over x, f prime is negative 1 over x squared. Okay, and this actually lines up with our power rule from before, and I want you to jot this down as well, that for f of x equals x to the minus 1, right? If I think about this instead of 1 over x as x to the minus 1, if I used the power rule here instead of deriving this, what would we have gotten? All f prime of x is the power negative 1 times x, and then we subtract 1 off the power, that's minus 2. So the power rule would have worked as well. All right, so as you go through this, and I encourage you to, so we did that one. I encourage you to do this guy and see that the power rule might apply on both of those as well after you apply the definition of the derivative. Okay, so in summary, some things to remember. For f of x, f prime of x is given by the limit as the time interval goes to 0 of this rate of change, what we call the difference quotient. F prime of x is a function. Okay, assuming that this limit exists, f prime of x is a function. And f prime of x is output is the instantaneous rate of change of f of x. And, you know, kind of as a minor note, that algebra will be the hard part, the challenging part, the interesting part. It's going to be what frustrates you the most, but that's not a reason to check out. It's a reason to refresh yourself, stay engaged, and review things that are rusty for you. It's happening to everybody, so don't feel like you're going through that alone. Okay. So have fun. I'll enjoy your questions in the class discussion, and we'll see you there.